Everyone, welcome back to my channel Computer Classes by Rachna. Today we will discuss implementation of the neural network, artificial neural network using KERAS. For this we are going to use one dataset which is MNIST. This dataset is basically handwritten numbers dataset. Just like you can see on screen, the handwritten numbers 4, 1, 0, 7, 8, 1, 2, 7 and 1. So these are handwritten numbers. So it's a huge data set having so many handwritten numbers, and we can use this data set to train the machine through KERAS, and we can basically get the output, and we can see whether the labels that are given for the image and the output that we are getting is same or not, and we can work on it. So basically this is the type of data set that will be there, and next you see are the function which are applied here. So this is how the output looks like, and how this image of a number, of a single digit number, is represented. You can see it's basically divided into pixels, and it's a black base, and on the black base the number is written with white. Okay, so this can be represented in the form of a matrix of rows and columns, and here we have taken a two-dimensional image. So this is two-dimension, means it is black and white. If it is three-dimensional image, that means it would be not black and white, it would be a colored image with RGB values. So since it is two-dimensional, which means these are grayscale, which also means black and white image. So let's imagine that this 2 is divided into a set of rows and columns this way. So how many rows you can see? 1, 2, 3, 4, 5, 6, 7. How many columns? 1, 2, 3, 4, 5, 6, 7. So 7 rows and 7 columns, and we have the white portion here. So basically all the values which are black are represented by 0. The color black is represented by the number 0, and the color white is represented by the number 255. So anything which is closer to white will be represented with a number closer to 255, and anything which is closer to black will be represented with the number nearer to 0. So this is how this 2 is getting represented in the grid form. And now what we have to do, we have to pass this set of values, which is 7 rows and 7 column values, into a particular format. So for that we will use the 7 by 7 grid, and we will flatten it. What is the meaning of flattening? Flattening means we will convert this 7 by 7 grid into 7 into 7 array, which becomes 49 length array into one dimensional. But you know, these images are not actually 7 into 7. These images are better when we convert them into a bigger grid, which means the number of pixels will be more when the rows and columns will be more. So let's say it is 28 by 28 for MNIST dataset. The actual grid size is 28 by 28. So we have to convert this dataset value of rows and column into a single dimensional array. So that means 28 into 28 dimensions array, that comes out to be 784 set of values in one dimension. Now we pass these values, and these becomes the inputs. So this is x1, x2, x3, x4, x5, so on, and the last value would become 784th value. So these are 784 inputs, and they will be passed on through some hidden layers, and then we will be getting the output. There are basically 10 possible outputs. How many possible outputs? 10. Since these are all single digit numbers, they can take the value of 0 or 1 or 2 or 3 or 4 or 5, so on till 9. So 10 possible outputs. From these 10 possible outputs, there would be a value which is generated. For example, the output for 0 is 0.29, the output for 1 is 0.07, the output for 2 is 0.92. This is the highest, if you will see. Since this value is highest, it means that the highest argument value is the actual output, which is 2. So this is how we get to know whether the handwritten number is 2 or the handwritten number is 3 or so on. So it's an array which is generated of 10 values, and the highest value we have to select. The corresponding index would be the digit that is represented in the image. I hope you understood till here. Alright, now this is what we will do. We will import. This is the practical aspect which you should know in theory also, that how we implement KERAS. So we first import TensorFlow as TF. From TensorFlow we import KERAS, which is just a covering layer which provides extra features so that working of TensorFlow becomes very easy through the functions that are present in KERAS. Then for plotting we use matplotlib. So we import the statement matplotlib.pyplot as plt. This is a screenshot that I've used for Jupyter Notebook. You can use this same platform, and then we import numpy as np, and we import cborn as sn. So these are the things that we import. Now after this, the most important thing is the data. So the data which we are using is a data set which is already present inbuilt in KERAS. So we use keras.datasets.mnist. So this is the dataset that we want, and we want to load it. So for this we use the function load data. Now where this data will be loaded? It will be loaded into this x and y. X means the inputs and y means the output. So x train and y train means the training data set, and x test and y test means the testing data set. So for training data set, when I'm using x train, it means the images which we are using for training the machine. Y train means output of these images. For example, this is one of the training data set, and the output of this data set would be 2. So x train would be this after conversion. So this is x train which we convert into single dimension, and this is y train. Now what will be x test and y test? X test and y test are also some images which are not labeled yet and which we are using for testing. Alright, so this is that data set that we are loading. This data set, once loaded, will have two set of divisions. One category is training data, another category is testing data. So the training data will be stored in x train and y train, and the testing data will automatically get stored in x test and y test using this statement. I hope it is clear. Now after my data is loaded, what I have to do? I have to use the length of x train. I have to display the length of x train. So this means how many data, how many images do I have for training in MNIST dataset. So length of x train is 60,000. The output is 60,000, which means there are 60,000 images for training. Similarly, I take out the length for x test. The length for x test is 10,000. So 10,000 images for testing the data. Then we do x train 0. X train 0 means the first element, the first image dot shape. What is the shape of the first image? 28, 28. So this grid that I was talking about, the shape is 28 by 28. So x train 0 dot shape is 28 by 28. Now I am, after displaying the shape, I am displaying the data. So x train 0, I'm displaying the values 28 rows and 28 columns, and since it is 2-dimensional, you can see there are 2 square brackets which will show because it's a 2-dimensional array. Alright, having 28 rows and 28 columns. After displaying this x train, I can view this as a plot. So plt dot mat show. Mat show means show the matrix. Which matrix? X train 0. So once we give the statement, the first value which is written is this. This is 5. and to check whether the label of this is 5 or not, the output of this is 5 or not, we can display y train 0. So once we give this statement y train 0, we will get the value for the output of the first image. What is the output of the first image? 5. Alright. Similarly, we can see the plot for x train 2, which means the third image. So the third image is that of a 4. And now you can see we also did y train 2, which is 4, which means the data which is given and the output which is given is correct. Alright. Now let's say we use slicing and we want to display the first 5 elements. So what we did, y train 0:4 is also possible, blank colon 4 is also possible. So it will show all the values, 0:5 and blank colon 5. It will show all the values from the beginning till 5 minus 1. This value n, let's say it is n. So the data is displayed from 0 to n minus 1. N is non-inclusive. Alright. So we get the values of the first 5 elements, which is 5, 0, 4, 1, 9. Then you have x train dot shape. Earlier I did x train 0, which means first element shape. Now I am doing x train dot shape. How many total images were there? 60,000. And for all those images, what is the shape? So 28 by 28. So this is the actual shape of the entire x train data. Now what we do is, since it is a set of values which is too huge to represent, the values are between 0 to 255 for all the pixels, I told you this. So to get the better result, we divide all the data by 255 so that I get the result which is closer to 0 and 1. So for this, what we do, we divide all the x train data by 255 and we divide all the x test data by 255. So we are just changing the values. If the value is 255, so 255 upon 255 is equal to 1. And if it is like 0, so 0 upon 255 is 0. So this is closer, and we will change all the possible values from 0 to 1 range. Alright, in between the range of 0 to 1 by doing this x train upon 255 and x test upon 255. So if you do not run this statement, what will happen? You will still get the result, but the accuracy will improve if you add the statement. So you can try all this without using this statement first and then see the output. And once you see the output, to improve the accuracy, you use this statement here, run it, and then redo all the statements which are remaining. You will see the accuracy will become better. Alright, now we talk about the flatten. I told you that we have to flatten the image. So let's say all the images that we flatten are put in flatten x train. So I put x train dot reshape, and how I'm reshaping? 60,000, which is the length of the x train. I can straight away write down 60,000 for all those 60,000 images. And for all those images, जो उनका shape है, the shape that they have 28 into 28, I have to convert that 28, 28 into 28 multiplied by 28, because I want to flatten that 2-dimensional array into 1-dimensional. So the shape becomes 784 in 1 dimension. Alright, so for that we give this statement, and then we give the flatten x train dot shape. So it gives me 60,000 comma 784. And now we move to x test. So we have to flatten x test also. So x test data we will flatten, which is flatten x test equal to x test dot reshape, length of x test, and then 28 comma 28. So what is the length? 10,000, and then 28 into 28, that would become 784. So we have flattened both the arrays x train and x test. Now I display the value of flatten x train 0. Earlier we were displaying the value of x train 0. There were 2 square bracket. Now you can see there is only 1 square bracket, which means it has been converted into 1-dimensional array. Am I clear? Now we just create the model. So this statement you might have to learn a bit. for now, then we can have the explanation in later classes. So first thing is we are building a model. So I can give the name model, I can give the name MD, I can give the name MDL. So it is a variable, it can vary, whatever name I want to give I can give. All right, now model equal to KERAS dot sequential because it is a model where one layer is connected to next and next. And then in the KERAS dot sequential, what type of model I'm creating? KERAS dot layers dot dense. I'm creating a dense model because it's ANN and all the input layers are connected to the all the next elements of the all the input elements of the next layer. So that is why it is a dense network. Now we give the size of the output. What is the size of Y? I told you there are 10 digits, single digits, so it is 0 to 9, which is 10. And then what is the size of input? The input size is input shape, which is equal to 784. That each image is now a flattened array of 784 comma. It means it's a one-dimensional array. And then what we have to do, we have to give the activation function. So the activation function which I'm using right now is sigmoid, because normally for binary classifier or for identifying the data into different classes, we use sigmoid function, and we can also use other functions, but for now let's take it sigmoid. All right, then after this we have to compile the model. So we have the statement model.compile, and optimizer is equal to Adam. Learn this for now because otherwise you will get a bit confused. So learn this for now, that we have to give optimizer equal to Adam, loss equal to sparse underscore categorical underscore cross entropy. So what is the meaning of this? Sparse underscore categorical, because there are different categories in which we get the output, right? If it was only 2, we could write sparse underscore categorical, but since there are different categories, we have to write down cross entropy along. Matrix that we want is accuracy matrix, so we have written matrix equal to accuracy. Then we want to fit this model, we want this model to learn, so model dot fit. And then how it will learn, we give the input through X train, we get the output through Y train. So flatten, X train is the input in the fitting of the model, and Y train is the output of those images. And then epochs equal to 5. What is the meaning of epochs? Epochs equal to 5 means how many times I want the machine to go through these input training data set. So since there were 60,000 training images, if it would have been one epoch, so the machine will go through 60,000 images once. If there are 2 epochs, the machine will go through these 60,000 images twice. If there are 3 epochs, the machine will go through these 60,000 images 3 times. If there are 4 epochs, it will go through these images 4 times. If there are 5 epochs, it will go through images 5 times. Because every time the machine is processing, it would take some time. So more number of epochs is more processing, but then we get better result. For example, when you have your exam, you revise again and again to get the result better. The more you revise, the better would be the result. The same way, the more the machine would go through the training data set, the better would be the result. So you can see the result here, that after first epoch, the accuracy is 0.81, which means 81%, then 91%, then 91.9, 92.2, 92.53. So that's the fifth epoch. After this, the accuracy has become much better. All right, now this is training. After training, we need to test whether whatever we have given the training to the machine has learned it or not. So for that we have testing. So for testing, we have model.evaluate. What do we have to evaluate? The X test and Y test. So this is X test and this is Y test. So now it shows that the accuracy is 91.36%. Now another example, that suppose we display plt.mat show. We want to show the matrix of X test. So what is the value of X test here? The value of X test is 7. So to see whether the actual value is 7 or not, we give Y predicted equal to model.predict flatten X test. We give the complete 10,000 images which was flattened to test. and we are putting all these into y predicted, which means the answer for y predicted 0 would be the output of the first image. Now I told you that the output would come in the form of this. Let's go back to the discussion. Output would come in this form, which means that an array would be generated with, if the image is of 7, it should have the highest value for 7, and for rest of the array these values should be low. Alright, so this is what we are going to check, whether the image that we have found in test, is it giving me 7 or not. Alright, so for this what we do, we take out the y predicted. You can see in y predicted it is showing me this 2.6, this is for index 0, then 3.21 is for index 1, 6.6 for index 2, 9.5 for index 3, 2.13 for index 4, 1.33 for index 5, 2.11 for index 6, and 9.9 for index 7, and 7.9 for index 8, and 7.14 for index 9, so on. So what is the highest value that we got? We got the highest value 9.9964, which is the index value of 7. Hence, the 7th position is the answer. So how to take this out? np.argmax, which means the maximum argument from y predicted 0, which is 7. I hope it is clear. So now we again do plt.show test 1. So in test 1 we have the image 2, and now let's see. Again we will take out np.argmax y predicted 1, and it will give me the output 2. Since it is giving me the output 2, whatever image I am testing, I am getting the actual result. So y predicted labels, how to get the labels for y predicted for first 5 elements that we took out earlier. So we do y predicted labels, np.argmax I for I in y predicted labels 0:5. So that comes out to be this. Alright, now in order to get the confusion matrix, we write down CM or confusion matrix, whatever you want, equal to tf.math.confusion matrix. So this is tensorflow.math, which is present as a library here, dot confusion matrix. We want the confusion matrix to be created, and then labels equal to y test, prediction equal to y predicted labels. So whatever we are testing and whatever we have predicted, we are looking at those, and then a tensor will come out, and which means an output will be the confusion matrix, which is displayed this way. Now since the confusion matrix is shown this way, we do not understand what it is representing. So what we do, we write down plt.figure, and then we give the size, it should be 10/7. We generate a heat map, and then we generate plt x label, which is predicted, and plt y label, which is truth. So the answer that we get is 95.72222% correct. And now we move further. So this is what we get as the result, 95.722. So this is how we have generated this, but we cannot understand this. We are not able to understand this tensor which is produced here as a confusion matrix. To view it in a better format, what we should do, to view it in a better format, we should view it as a heat map. So the statement for heat map, for that we have taken Seaborn as Sn. So plt.figure, the size of the figure is given, from which you have to take the data, and then Sn is Sn.heatmap, a heat map to be generated. Cm comma not true, fmt equal to d, plt.x label is predicted, plt.y label is truth. So predicted values and truth values we want to see. So in text the answer is 95.722.05, and then we have the y label for the truth value. So it is truth value, which means it predicted correct. Alright. So this is just a way to create a heat map. You don't have to get into all the details right now. Just see that a heat map is generated, and then this is the heat map which is generated, and you can see different set of values which is given. All right, so to make it better, we can add another layer. So first layer we are adding ReLU layer. So model equal to keras dot sequential, keras dot layers dot dense, activation equal to ReLU, keras dot layers dot dense 10 input shape, this activation equal to sigmoid. We are adding two layers. So this one is a new layer which we are adding to the same model. It's a hidden layer that we are creating. Everything same, just we are adding two functions. One is ReLU, another is sigmoid. And after this, we compile the model, we run the model the same way, we evaluate the model, and you can see the accuracy increases. All right, so I hope you have understood this working of ANN using KERAS. Thank you so much.